Je suis content d'accueillir Anders SOGAARD ici à Montréal aujourd'hui. Il est professeur universitaire. Un instant. Monsieur, est-ce que vous voulez fermer la porte s'il vous plaît?
Oui, absolument.
Merci. Anders SOGAARD de l'Université de Copenhague, professeur universitaire d'informatique et de philosophie, et il dirige le nouveau centre de philosophie de l'intelligence artificielle. J'ai tout de suite lui demandé qu'est-ce que c'est que la philosophie de l'intelligence artificielle à l'Université de Copenhague. Il est connu principalement pour ses travaux sur la programmation des langues naturelles multilingues, l'apprentissage multitâche et l'utilisation de données cognitives et comportementales pour biaiser les modèles de PNL. SOGAARD est lauréat d'une bourse de démarrage du Conseil de recherche de l'Europe, ERC, d'un prix de recherche ciblé Google. Il est auteur de Semi-Supervised Learning and Domain Adaptation for NLP de 2013. Intégration de mots multilingues et traitement du langage naturel explicable. Son titre, le titre de son séminaire est les LLM, indication ou représentation. Maintenant, Anders, I want to ask you a few questions in English before you start your talk.
Sure,
what
no
do you
problem.
mean by indication versus representation?
Right. So I'll get to this, but
Okay, I'll let you do it in your own time. That's good.
That's
And the
cool.
other question is, what is your department is philosophy of artificial intelligence. So are you a philosopher or are you in artificial intelligence?
Neither or both.
Neither?
I don't know. So I'm a professor at computer science department 4 days a week. I spend 1 day a week with the philosophers here, and I have something called the Center for Philosophy of AI, which is primarily placed in the philosophy section, but is supposed to sort of build a bridge between the two.
Very good. Who's Steve? Steve Hansen, can you turn on your sound and tell me whether you're hearing things correctly in New Jersey? Well, I'm not saying anything that maybe he's not hearing. Chris,
Oui, on entend bien. Je reçois 5 sur 5.
Okay, very good.
Ou 10 sur 10, ou 20 sur 20.
Okay, c'est beau. So, it's yours, Anders.
Very cool. Okay, so...
Oh, sorry, one thing I forgot. Did I ask you whether you want questions during or after your presentation?
I can do both. I mean, I'm here for you, so feel free to interrupt, and we can also do questions in the back. So
Very good. Now, this time it really is all yours.
Okay, very cool. Yeah, I'll get back to the title, but basically, it's sort of about what do we mean by, when we talk about LLM representations. I guess the main question that I'm interested in here is twofold. So I'm interested in, when a language model uses a word such as cat or chopstick, does it actually talk about cats or chopsticks in virtue of some model, some understanding of what it means to be a cat or a chopstick? And if so, could language models, in principle, instantiate the kind of cognitive capacity that we associate with understanding? The kind of position that I want to try to argue for here is very naive. It's an internalist position, and I kind of secretly hope to be proven wrong, but I'll present some empirical arguments that I think speak in favor of such a pretty naive position, and I'll discuss some of the more famous kind of counter arguments against such a position. But I want to start with sort of what a language model is, and of course this is roughly what a language model looks like these days. We have this prompt, we can talk to them, and it kind of, it feels almost like talking to a person. But of course, most of us and presumably most people hearing this talk will know that sort of behind the scenes here is a neural network. And a neural network is really just a function. A neural network learning algorithm is a function estimation algorithm. Now, what's function estimation? So we probably all did this in elementary school. You have, say, a sequence of input numbers and a sequence of output numbers. This could be 1, 2, and 3, and maybe 11, 12, and 13. And you're asked sort of to figure out what function takes you from the input to the output. So from 1 to 11, 2 to 12, and so on. And you do this sort of fitting. You figure out what the function is. In this case, something like f on x equals x plus 10, maybe. Now, the nice thing is that once you have that function, you can throw more data at it. So we can throw, 4 at the function, we get 14 out, we can throw 5 at it, we get 15 out. And so we've learned a function from limited data. Now, that function is not in itself a chatbot, but the trick is simply to associate some words with numbers. And if we say, cat is 4 and cute is 14, or 5 is dog and bark is 15, we got ourselves a little chatbot. If you say cat to it, it'll respond cute and so on. And of course, in reality, these language models will learn probability distributions over vocabulary, but that's really just a technicality. And of course, this is also a very kind of simple chatbot in the sense that it will respond in one word only. The trick here is, though, simply to apply the same function multiple times. So if you have this function, f on x equals x plus 10, you throw 4 at it, you get 14 out, you can make that the input. You can throw 14 in, you get 24 out, you get 34 out, you get 44 out, and so on. And if all of those correspond to words, you can generate sequences of words by using this function. Of course, again, the story is a little bit more complicated in that these neural networks are compositions of functions. So we have multiple functions inside the guy here. So this could be something like, f on x with x plus 2, and then g on x equals f on x plus 8, for example. So in this case, you have a function whose output becomes the input for another function. And you compose all these functions, you get an architecture, and these large language models have these transformer architectures, but basically most of the math is sort of the same. So neural networks, chatbots, language models are just functions, and that doesn't look intuitively like the kind of thing that would know what a cat is. On the other hand, when you talk to this prompt, it feels like something that knows what a cat is. And that kind of paradox has led to what people call the LLM understanding debate. I think maybe that's Mitchell's a term. And it's basically about whether these large language models exhibit some form of understanding when they use words like cat and chopstick. Do they know what they're talking about? Do they have an understanding of the world we live in, basically? There's a lot of logically possible positions you can have in this debate. I think I've identified 5. Maybe there's more. I'm happy to hear about the positions that I missed. One position clearly is the view that these models they really don't have semantics. They're just all syntax, no semantics. In the words of Emily Bender, they stitch tokens together without any reference to meaning. And there's a bunch of arguments for this position. There's at least 2 classes, Leibniz-Mill type arguments, basically just sort of pointing out that these are functions, and kind of like Leibniz stepping into the mill, you just like, where would you have semantics in the system? The other type of argument, I think, is, kind of like Searle's Chinese room or Bender and Kohler's octopus. And there's quite a few people taking this position, Bender and Kohler, but also I think Gary Marcus, for example. There's another position which is very similar to the first position, but that acknowledges that large language models certainly can, infer in the sense that they can make entailment decisions or paraphrase decisions. So they learn relationships between words, endowing them with inferential semantics, so not referential semantics, but another form of semantics. This is Marconi's distinction between inferential and referential semantics. And I think people like Bill Rappaport and Chris Potts and Piantadosi would have this position. And to some extent, the difference here between 1 and 2, I think, is sort of a little bit a matter of where you draw the line between syntax and semantics. The third position, and the position that I'll try to argue for here, is that these large language models, at least in principle, can have referential semantics, and by internalist means. So large language models learn in an auxiliary fashion these world models that enable them to refer in virtue of such models. This comes out as a byproduct of predicting the next token, because it's simply a good compression strategy. If you want to memorize the entire internet, that's not going to be possible even with billions of parameters, and having a world model is just a very efficient way of making a lot of things very predictable. I think roughly this is the position of Eli Pavlik. I've presented arguments in favor of this before, and I think someone like Mark's Techmark would say something like this too. Again, I'm sorry if I'm misclassifying someone here in this taxonomy. There are other positions that are sort of more externalist, saying large language models do not refer in virtue of representations or world models, but in virtue of taking part in communicative practice or conversational games. I think Herman Kaplan and Josh Dever in their book, Making Sense of AI, are saying that large language models would exhibit some form of understanding by virtue of taking part in such practices. Other people have claimed that this only holds for large language models that have learned from human feedback and actually sort of participated in such a game. So people like Budlin and Mollo would say large language models do not exhibit understanding, but chatbots potentially do. What I want to talk about here is some arguments for preferring position 3 over position 1, or maybe position 1 and 2. And so this is sort of very briefly put the stochastic parrot view versus, I think maybe Stephen introduced this idea of, or introduced the term Platonic models for something like position 3. So I'll use that as a drawing here. And I kind of like that term because there's still a sort of a projection step missing to part of the story that I'll get back to. Kind of like with Plato. Okay, so we know that these large language models are functions, but I want to talk about them as models. So how do we get from functions to models? That's fairly simple. These models learn these transformations. So you got an input space of how the data is represented, but there's a lot of transformations happening inside these large language models. So when I talk about models, I talk about how things are represented in the feature space. I'll mostly talk just about the token representations and not about sentences and texts. So a model here is the representation at, say, a hidden layer of the model. So it's fairly simple.
Can you hear me?
Yep.
Okay, I would like to ask you a question. First of all, I would say that a minority of your audience is philosophers, and the majority of them are not philosophers. They may be psychologists, computer scientists, linguists, etc. So with that presentation that you gave about referring, would you be kind enough to define what you mean by referring?
Yes.
Not
so
referring for a philosopher, but referring for someone else.
Right. Yeah, it doesn't have to be super technical. So again, I'm interested here in whether large language models, when they use words like cat and chopstick, actually talk about cats and chopsticks, whether they have sufficient, whether they would be sort of capable of sort of pointing to, a cat walking by in some sense, having a sufficient understanding that it could, in principle, be projected onto, say, perceptual representations such that it could sort of map words to reference.
Representations there is a bit of a weasel word. There's a world, okay? And if I say cat and refer to cat, there's a furry thing out there that I am able to identify. Are you calling for that?
Yes. I'll get back to sort of different ways that representation that's a term that's been used very differently by different people. I'll get back to some of the, but I'll end up arguing for large language models being able to identify cats in virtue of how they relate to other things. So it's sort of a
in virtue of what? The other thing I wanted to suggest to you is that your English is excellent, but you're trailing off at the end of every sentence, and people, especially people who don't understand English that well, but even they're not going to hear it. So I suggest you speak more slowly and watch the ends of your sentences. Okay?
I'll do my best. I'll do my
Oh,
best.
sorry now that we're completely in the virtual world, I have to handle it.
I appreciate the feedback, and yeah, doing all these things virtually is complicates things. So it's nice to get feedback. Cool. Okay, so what I want to present here is first some.
Just a second. We also have a question from Steve. Steve, is it because you want to ask a question? No. Okay, I guess his hand is up for nothing. Excuse me for the interruption.
Oh, no worries. No worries. Okay, so again, I want to try to present some arguments in favor of this view that language models actually learn or induce, as sort of a side product, representations or models of the world, and that when they use words like cat and chopstick, they at least possibly can pick out those words in virtue of some understanding of what these words mean. And I'll start with, and then I'll get to some of the potential pushback against that kind of view. The first argument that I want to present is inspired by this paper that I assume you read, or most of you know, from Bender and Kohler. The paper called Climbing Towards Natural Language Understanding, famous for this thought experiment about the octopus cutting the cable between two people on deserted islands. That thought experiment in itself is a bit vague, but there's a second thought experiment in the paper that's much more concrete. So I'll talk about that. So Bender and Kohler imagine a system in which two models are trained. One is a language model trained only on text, and the other model is a computer vision model trained only on images. A language model is trained, again, so a language model, again, is a function from context to text. It's trained by doing fill in the gap, predict the next word. The computer vision model is trained in the same way. So it's you do this sort of predict part type training where you take an image, you remove a pixel patch, and you try to fill in the blank. The thought experiment goes as follows. If you have such a system, so you have one model trained on text only, one model trained on images only, completely disjoint data, would that system be able to do what's called visual question answering, so where you're presented with a sentence and an image, and the sentence refers to what's in the image. So for example, how many dogs are there in this picture, for example? Would such a system be able to do that? And the thought experiment is just supposed to appeal to your intuition that obviously this is necessarily impossible. What I want to say here is that I think that's an empirical question. And I want to present some results that suggest it's an empirical question. A few reasons to think it's an empirical question is that we've solved similar problems in the past. So in cryptography, sometimes we've been able to map two things that are disjoint. And certainly, and this is the more direct connection in unsupervised machine translation, we've done this. So there's a couple of ways that you can do unsupervised machine translation. And the kind of method that I'll be inspired by here goes back to work in 2016, 2017, where people started to see that when you train word embeddings, so say you train word embeddings on English Wikipedia, and then if you train with an algorithm like word2vec or glove or something, and then if you train word embeddings on another language, say Hebrew Wikipedia, they exhibit the same geometry in the sense of, if you take all the vectors of vocabulary, an English vocabulary, and you take the corresponding words in Hebrew, and you look at the vector cloud or the point cloud that you would get from just embedding these words, they tend to have similar structures. And what you can do is basically play Tetris with these structures. And without having any form of supervision, you can sometimes align these structures if they're similar enough, such that basically things match. And for some language pairs, at least, these matches are super, super good. For some languages, 9 in 10 words will end up right next to their translation equivalent. For other languages, it's going to be more like maybe 40% or so, but this is enough to get you started building an unsupervised machine translation system. So the next step is a lot of bootstrapping and building two translation systems at the same time in opposite directions. But the core step is just seeing that the geometry of how things are encoded is similar, and similar enough that you can do this mapping. So the alternative to doing this in a fully unsupervised way is just to have a little bit of supervision. So there's famous results where you show that just knowing that like where the numbers are is enough to align these also very efficiently. That kind of work inspired us to sort of question Bender and Kohler's thought experiment and just try to do the same with language models and computer vision models. So computer vision models come in different flavors. Some are supervised, like the ResNet models, for example, and others are unsupervised, just trained on this sort of pixel patch prediction task. And so what we did was we took a concept list, in this case, the ImageNet 20K list of concepts. You get some images from, say, an image search. You embed the images, you get a vector out. You do that for all 20,000 concepts. You can do the same in a language model. Actually, we complicated the task a little bit by taking 100,000 concepts as our target space. And then we try to see whether aligning these spaces, the 20,000 concepts in the computer vision model and the corresponding 20,000 words in the language model, would be enough that you could retrieve good words for images among the 100,000 words. Okay. So again, the idea is that, you know, if these models learn things, organize things in the same way, maybe the shapes are so structurally similar that we can do this kind of alignment. And it turns out that you can do that with very little supervision. So with just a few dozen pairs of supervision, you can align these representational spaces such that when you present, you know, a computer vision model with, for example, pictures of an udder, and you apply this linear projection that you've learned by playing Tetris, so basically by aligning these conceptual spaces, the nearest neighbors will be words like river otter, otter, sea otter, and so on. In general, the structural similarities are, or the spaces are more similar, the better the language models are, the bigger the language models are. And, you know, you can evaluate this in different ways. You can look at whether an image ends up right next to the label that you happen to have in ImageNet 20K. As you can see here from the examples, a lot of these words in the nearest neighbor space are near synonymous. So I think it's probably better to maybe look at something like precision at 10 scores, because they tend, like a neighborhood of 10 words in a language model, you know, tends to be just a neighborhood of synonyms. Or maybe it makes sense to look at precision at 100, because that's going to be a semantic category, a rough approximation of a semantic category. So basically, these results suggest, so we got the size of the model on the x-axis here, and we got the precision scores on the y-axis. And what you see here is that for the MAE models, which are unsupervised computer vision models, the different language models align so well that for about 2 and 3 words, you end up, or about 2 and 3 kind of images, you end up with having the exact label in a neighborhood of 100 words. So that would mean that you end up with the right semantic category.
1 second, Anders.
Sure.
There's a question here. I have to mediate because I can see him. And
Sure.
Go ahead.
Sorry, you may have already said this and I just didn't catch it, but could you say what MAE is?
So MAE is an unsupervised computer vision model. I don't think yeah, no. So as you can see on this table, we did experiments with different models like the SecFormer and the ResNet, and MAE is just another one. MAE is perhaps more interesting here because it's fully unsupervised. The ResNet model is trained to label images, and you could potentially argue that introduces a bit of a language-like bias. So we're sort of paying more attention to the experiments with MAE because it's fully unsupervised. But yeah, so it's really just like it's kind of like a large language model, except trained on images on this pixel patch prediction task. So what this shows is just that there's a lot of structural similarity. I mean, we are mapping into a target space here of about 80,000 words. So you know, if there was no similarity between these spaces, You know, a random mapping would just give you a score of, you know, precision at 1 score of 1 over 80,000, you know, precision at 10, 10 over 80,000, and so on. So these are much, much better than random. And in fact, so similar that for 2 and 3 words, we end up in the right semantic category. And for about 1 and 2 words, we get a concept that's synonymous with the label in the concept list that we started with. So I think this suggests that there's a lot of similarity between what a language model and a computer vision model would learn. And I think the only real explanation is that they're learning something about the world that's sort of generating the data. But in the context of the Bender and Kohler experiment, it shows that unsupervised kind of mapping between these spaces is in principle possible, and that it's an empirical question and not necessarily true that this would be impossible, I think.
Anders, could you say in a few words why it is that you have more confidence in the unsupervised learning than the supervised learning, and why you say that the supervised learning is language like, or the unsupervised learning is something else like?
Oh, I didn't mean to say that. The reason that I promote the experiments with the unsupervised computer vision model here is just because that aligns better with the conditions in the thought experiment by Bender and Kohler. So in the thought experiment, there's supposed to be no relation between language or text and images, and you could argue potentially that the resonant models, because they're predicting these labels, is biased by some supervision between image and text. So in order to kind of avoid that pushback, I'm focusing on the unsupervised models here. But the results, by the way, are very, very similar across the 3 different computer vision models.
Okay, but what that means is that by supervised learning, you're thinking particularly on supervised learning and associating with one thing with a name.
Yeah.
Okay. It doesn't, but there's other kinds of supervised. You can do supervised learning for all kinds of things, like an action or even a nonsense syllable.
Yeah. That's certainly true. And I mean, the sec-former models that we use here are sort of scene parsing models. So they're a little different. And again, I think the story is that you know, with enough training data, they tend to these by the way have some very similar representations of the concept spaces, these computer vision models. So I think in some sense the objective, you know, the exact objective with enough data doesn't matter too much, it seems, in terms of how concepts are organized in these models. This table here I brought just to sort of remind you that in this experiment, of course, there's a lot of noise. I mean, a lot of these labels, a lot of these words are polysemous, and of course, results are better if they're not. And a lot of the images will have a lot of dispersion. So I showed you this image of a ship here. The label here is Latin sail for some reason, and you know, I guess it could have been sailboat. And these are factors. So we get better results if dispersion is low in the images and if the words are monosemous. But still, you see these very, in my view, remarkable structural similarities, suggesting that these models do use the strategy of learning something that looks like a world model as a way of learning how to predict the next word.
Quick question, if you can hear me.
Go ahead, Steve. Just speak out loud. I can't communicate with you, but just speak.
Can you hear me now?
I hear you just fine.
Anders, can you? Oh, good. So the alignment kind of format or idea you have there is interesting, but how do you do this in the absurdly high dimensionality of the space of, you know, like the autoencoder you're talking about, masked autoencoders and the, well, just, you know, the LLMs. If you have, you know, let's guess 10,000 hidden layers with a few thousand per head, the question is first, where do you look for the alignment? If you're going to do something like Procrustes, right, in terms of principal components, or we take and we align to, or even multidimensional scaling, you align two spaces together. That's meaningful in my visual system in 3 dimensions, and maybe I can fake 4, but I'm not sure I can get to 10,000. So there's obviously some projection ideas here. You have to do this.
Yeah. So what we do is, so we've been inspired by work in unsupervised machine translation, as well as work on in neural encoding or brain encoding and brain decoding. So we use a couple of different methods. So we use procrustes analysis, and we use basically just regression models where you sort of have a regression model for every target dimension. And then we've done experiments with, the unsupervised experiments we do are with generative adversarial networks, kind of like an unsupervised machine translation. So the representations we extract and then we use, also determining the dimensionality of the space here, we've done it different layers. So I'm kind of cutting the story short a little bit here, but in the papers we have results for typically, a lot of different layers in the language models. So we look at what happens at the embedding layer, what happens kind of up the language model.
Yeah, there's still an issue of shape, and I think it's an interesting one with regard to LLMs, which, at least in the OpenAI literature that I gotten a hold of, it appears that there's somewhere between 50 to 100 million clusters in a standard, let's call it 300 billion sized weight system. Those cluster spaces would seem to be a target for alignment probably in the sense that you mean, but in the sense that I mean in terms of working on what context means here.
Yeah. So that's okay. So that's a good question. So we don't align. So so there are two questions here. One is, okay, so we have all these concepts. You can throw them in a language model that's trained to do stuff in context. We have a couple of different methods in our papers. The results that I'm showing today, we just basically present these words sort of as standalone words. You can also try to sort of average across a bunch of contexts, or you can create some templates to sort of get minimal context or something like that. We don't actually embed them with their full activation. We embed them at different layers. So we basically take out their representation in a particular slice of the neural network. So the dimensionality here is typically going to be in the thousands and not in the millions or billions.
Great. So please go on.
Cool. So the second kind of result that I wanted to show here is a very similar experiment, but where we use knowledge bases and not computer vision as the target space. And so again, the experiment is very similar. So we take something like Wikidata, and then we use a graph embedding algorithm to get a vectorized version of Wikidata, where basically every QID in the database is associated with a vector. And then we see whether the geometry of the language model is similar to the geometry of the knowledge base, or the vector representation of the knowledge base. And again, we see the same picture, that the better the language models are, the bigger the language models are, the more they align with the geometry of the knowledge base. So the results here are something like, for a precision at 10, for example, with some of the best models, every second word is going to end up in a neighborhood of 10 next to its QID when doing this linear mapping. And again, we use experiments. We do experiments with procrustes analysis and linear regression. In this particular case, all the experiments were kind of minimally supervised with a few dozen links. And again, suggesting that the geometries here converge toward being very, very similar. And again, I think this is sort of supporting this idea that that having a world model is a good compression strategy for these language models, and it sort of falls out in some sense of this task of just having to predict the next word. The third kind of results that I wanted to mention, I think you've probably maybe Ellie talked about this earlier in the course, and there's a lot of examples out there, kind of a more anecdotal nature. So we've done this with color terms and directionals, and other people have looked at other things. This is an example from a paper by Max Tegmark, where he's basically just embedding geographical terms, and then he's projecting. He's taking out the representations, again, with a few thousand dimensions, projecting it down to 2D, aligning it with a map, showing that there's a kind of trivial correlation between the structure here and the map. And And again, this is more anecdotal evidence, but again, suggesting that these models learn something that looks like models of some facts of the world. Now, I wanted to mention kind of a second thing, which is maybe more speculative, but just because the experiments are very similar, I thought it'd be interesting to mention here. We've done the same types of experiments with neural response measurements. So idea is you put people in brain scanners, you have them listen to a podcast or read Harry Potter, and then you take the fMRI signal, and we use something called a Gaussian smoothing to basically extract word representations. And then again, you get a point cloud, you get a vector cloud, and you can try to see whether it's structurally similar to the corresponding word cloud you get from a language model by inputting these words. And again, you can do this, in the same context that you have, or you can look at standalone words. And again, you see this sort of effect that these large language models enable pretty good precision against these linear projection matrices or over these linear projection matrices. And here the results are something like for every 1 in 2 words, we can extract sort of the concept that people were exposed to through reading or listening. Just suggesting that maybe these organizations, these models also have structural similarities with activities in the brain, but of course here there's a ton of noise in the experiments. One interesting thing I wanted to mention, because maybe this is relevant for the discussion around sort of more externalist positions in this debate. We did this experiment with instruction-tuned large language models, comparing a large language model before and after instruction tuning. And very, very consistently, what we see is that the instruction-tuned large language models do not exhibit more structural similarity with computer vision models or knowledge bases, but the instruction-tuned models do exhibit more structural similarity with the neural response measurements. So maybe that's a window of opportunity for externalists here, because the only difference here is that these models have participated in these conversational games, so to speak. And here I have some more plots. So these are the kind of experiments that we've done for, in all these cases, kind of extracting representations at different layers, seeing what sort of happens at different layers. Results across different data sets and across different projection methods. I mentioned in the start that I mean, what we're showing here is just that these large language models learn to organize things in a way that have structural similarities to other domains. So we actually don't get aboutness, we get a structural similarity. And the question, of course, is kind of how do you project onto another type of representation? So if you have your representations of perceptual stimuli, for example, olfactory representations or tactile representations or auditory representations or visual representations, how do you map onto those? In practice, how would that come about? And I think there's a couple of you can call it theories. If we talk about humans, you can call it sort of approaches or methods. If we talk about large language models, one kind of theory for how this could happen is that we have a little bit of submission. So there's a little bit of a pointing game making this possible. Another theory would be that this happens by something like this unsupervised point set registration that I talked about. Now, the problem with that as a theory for how understanding or meaning comes about in humans, of course, is that it would predict that there would be sort of this eureka moment relatively late in language acquisition where the kid had sort of, subconsciously processed a lot of words, organized them, and all of a sudden the organization is good enough that it maps onto the perceptual representations, for example, and then all of a sudden the kid understands all the words. And as far as I understand language acquisition, that's not kind of how that works. So probably theory 2 here is not true of humans, but it may still be a methodology for grounding a large language model, of course.
Could you repeat your definition of the pointing game per se, so I know what the paradigm is?
Right. So the pointing game here would just be the kind of supervision that would link, for example, a few words with their reference. So, the word banana refers to that thing over there. And in the case of the computer vision models, it could be a picture of a banana. In the case of if the target domain was a knowledge base for some reason, it could be the QID and so on.
So if we could get back to what you said to me before, reference in the sense of when I say cat, referring to a cat or that cat out there. In the pointing game, what is the thing that's being pointed to?
Right. So you mean in the context of human language acquisition?
I'm just talking about what you called the pointing game. What is the paradigm? What is
Right.
device
So
has to
here
do?
I'm trying to sort of be a little agnostic as to whether we're talking about humans or language models. So I'm just assuming that there's a target domain of some sort. So there's another type of representation. So you got the language model has induced a representation, a model, and you want to know what sort of maps on or what maps to what relative to another target domain. And the pointing game here is just having access to weak supervision.
What? Sorry.
It's just having access to some sort of weak supervision signal that would enable you to draw or connect a few points in your source space, the large language model space, with whatever target domain you're interested in referring to or in virtue of.
What if the target domain is not a representation, but a thing in the world? And what I'm pointing to when I invoke a word, cat, there's a thing in the world called a cat, and pointing to it means having a device with which I can see, feel, or touch the cat and touch the right thing.
Maybe 3, right?
Right. So, I mean, the target space could certainly be a physical space. So I would prefer not to get into the sort of the complexity of I mean, so when these models, or when models in general, maps are isomorphic to something out in the world, they can be isomorphic to different dimensions of the world, right? And I think that's all we need to basically establish aboutness or some way in which language models can be said to refer to cats and chopsticks in virtue of a model of what it means to be cat and chopstick. It doesn't have to be more than just some dimension of, and yeah, this could be a representation of reality or reality itself. But it doesn't have to be.
From what I've understood of what you said, it's always just representation to representation. I don't see how the cat gets into that.
Yeah. Okay. So maybe it makes sense to talk a little bit more about this when we get to some of the pushback and some of the counter arguments, because I think
just brought it up now because you're on grounding, and this is what grounding.
Yeah, sure. So I think there's a question here of how we define representation and how to what extent representation is. So one of the things that I'd like to discuss, because it's often brought up, is whether representation is something that's symmetric. Because if it's and most people assume it's not, and I want to argue that maybe it is, and if it is, it doesn't really make much of a difference, right? Whether it's representations or, because everything that's represented is also a representation of the representation, and I think that's sort of maybe an important discussion for resolving this question. Does that make sense?
Sorry, go ahead.
Cool. I'm happy to talk more about it. Yeah. And this is maybe in general sort of the part that I haven't wrapped my head around. So I would love to talk more about it. Anyways, so the theory 3 here for how this could happen in a system, and I think we're seeing similar things happening in language modeling systems, is that this basically just happens automatically by compression when you have some sort of multimodal training. Okay, so if it's true that a computer vision model, for example, and a large language model will converge toward structurally similar representations of concepts, it will also be economic for a multimodal model to use similar encodings for the concepts across the different modalities. So basically map onto the same representations. And we're seeing that for example, in multilingual models. So if you take something like mbird, a lot of words are represented in the same way across languages if they mean the same thing. So in order to avoid redundancy, a model can, pressured sort of by a need to compress as much information as possible in few parameters, do this alignment automatically. And of course, that doesn't mean that that doesn't rule out weak supervision. So you can have both. And there's a lot of multilingual models, multilingual language models that are trained in this way, where you use a little bit of supervision to sort of promote this form of alignment. But you also see it when there's no such supervision. So I think these are at least 3 ways that you could have this kind of projection come about, either through supervision, through unsupervised point set registration, or just by compression as a side product of compression, basically because these models have too few parameters to encode the training data. And I think it's sort of, we're seeing all 3 things being possible in the language modeling space. And of course, the question is whether any of these would be feasible in a biological system like a human being. Okay, so I want to briefly pause for a moment and talk about representations and why I think it makes sense to talk about language model representations as representations in the more philosophical sense. Representations here, token representations, are just these points. So they kind of don't look like classical representations, and I think it's important to sort of point out why they are much like classical representations. So indication is how, a word like cow in a language of thought type theory is represented by an indication. And so the representation of, or the indication of cow doesn't actually come with explanatory power. Now, an indication is source dependent. So one example would be a thermometer, right? So a thermometer indicates temperature. It's source dependent in the sense that if I take a thermometer and I put it in the fridge, it's going to tell me how cold it is in my fridge. If I put it on my porch, it's going to tell me how warm it is on the porch. Now, representation, say a map of Sweden, if I put that in the fridge, it's going to be a map of Sweden, but if I put it on the porch, it's still going to be a map of Sweden. So it's source independent. Now, a large language model token representation is also source independent, but it's collectively source independent. So if I take the conceptual space of a large language model and I put it in the fridge, it's still the same conceptual space. And if I put it on the porch, it's still the same conceptual space. But if I take the individual token representation and I put it in the fridge, it doesn't mean a thing. And I think that's confusing a lot of people. And this is because what's really important here is the second order structure in this space. And I'll get back to that. So indication in a language of thought type theory is arbitrary. Whereas in a representation-based theory, the representations are structured. Now, the large language model token representations are just, in some sense, points in space. So they don't look like something that has structure, but obviously they do. A point in a 1,000-dimensional space is a data structure. It's a dictionary with feature value pairs, 1,000 feature value pairs or 10,000 feature value pairs, and that is a structured representation. And while indication again is contentless and doesn't do any explanatory work. And so in a language of thought type theory, you need to go to your proposition bank to learn something about cows. Representations are supposed to do explanatory work. And it's important to point out that these LLM token representations also do that, because these dimensions that you have in language models can mean things. Sometimes it's sub-symbolic. It's hard to kind of label the dimensions and label their meaning. Sometimes you can do that. And I wanted to talk a little bit more about that. These are some nice drawings by Brian Orr about different sort of senses of representation in philosophy. To someone like Aristotle, representation was an image of the thing represented. So there was a first order isomorphism between the mental image and whatever the mental image referred to. And it was the same for Berkeley and Hume. That's not the kind of isomorphism that I'll be interested in. That's not the kind of representations that you have in language models. Hobbes had a different type of representation in mind. He had a representation that looks much like a sort of feature attribute or a feature value structure. And I think that's much closer to what happens inside a large language model, except that a lot of the dimensions here are not going to be interpretable. But I do think that what we're seeing is that the bigger the models get and the better they get, more and more dimensions become interpretable. So we're sort of maybe converging towards something that looks Hobbesian. But of course, the kind of representations that we have in mind here are Hebbian or connectionist. And for those, Hobbes as well as Hebb, what's really at stake here is a second order isomorphism to what you're modeling or what you're talking about. And the question, of course, is whether that's sufficient to establish a form of referential semantics, a form of aboutness, so that you can say that, when a large language model talks about a cat, it actually has an idea of what a cat is. And there's some classical arguments in the literature against that idea. So the idea has been proposed many times in the history of philosophy, but the classical arguments, two important ones come from Newman and Goodman. Newman talks about how isomorphisms are in general trivial. So that sounds like you don't want to appeal to isomorphism. And Goodman has pointed out that isomorphisms don't seem to have the right properties to capture representation. On the other hand, there's people arguing for isomorphisms in the context of aboutness or referential semantics. People like Ron Shepard or maybe Kenneth Craik. One advantage of these second order isomorphisms is that it's sort of easy to see how they could be implemented in neural activations, unlike the language of thought theories, for example. And someone like Kenneth Craik has pointed out a very long time ago that there's reason to believe that such structures could fall out of prediction. And I think people in predictive coding or the people interested in the free energy principle would say something similar. So there's like arguments for and against them. I'll try to talk a little bit about the arguments against this view. So Goodman, in the context of discussing art and aesthetics, talks about isomorphisms and how they seem to have different properties from how we use representations. So isomorphisms are symmetric. So if A is isomorphic to B, then B is isomorphic to A. They're transitive and they're reflexive. And representations do not seem to be used in that way. The question, though, is whether Goodman is sort of talking here about how we use representations or their formal properties. So, for example, a paperclip is mostly used to align papers. That's how we use it in practice because we're interested in aligning papers. But it has properties that would enable a paperclip to stitch papers together in all sorts of ways. So the fact that we tend to use a particular thing in a particular way doesn't necessarily say much about the formal properties. And I want to push back against the idea that representations are symmetric just a little bit, or at least it's super intuitive why representations are not symmetric. So here's a model boat, and that model boat represents a boat. And it's nice because you can put the model boat on your desk and you can think about the boat. And a map, represents a landscape. And that's great because it's a handy way of, talking about a landscape and drawing inferences about a landscape. But what if I think the reason that it works this way is because we tend to be interested in boats and landscapes. But what if we were interested in the models here? What if we were interested in the model and the map? So say that the model was done by Leonardo da Vinci, or had the size of a sewing needle tip, or had gotten lost. And we wanted to know something about the model, but we still had the boat. Wouldn't it make sense to go and take a look at the boat to draw inferences of what the model would have been like? If the map was drawn by Leonardo da Vinci, or had the size of a sewing needle tip or something, and we were really interested in the map, but we didn't have access to it, the landscape would be a place to go if we wanted to draw inferences about the map. And here I think the landscape is representing the map, enabling us to draw inferences about the map. And the same for the boat and the model. Similarly, I think, it's not intuitive to me, at least, that representations are not transitive. So one example in which it seems that representation is transitive is take this book by JFK, 13 Days, which is a representation of his perspective on the Cuban Missile Crisis. There's a movie version of that representing the book, arguably, but that is, of course, also a representation of JFK's portrait of the Cuban Missile Crisis. So I realized there's more complicated experiments. So you can say that a data structure can represent an image that can represent a doc, but it's not entirely clear to me why we want to say that that data structure does not then represent the doc, even if we can't kind of see it. So we're not maybe interested in using representations this way because it's a bit of a gap, but it's not clear to me why we don't want to use the word representation here. Also, it's not intuitively clear to me why we want to say that a map is not a representation of itself. And I think maybe Goodman's challenge here ties a little to what you said before, Stephen. The other argument, which goes back to Newman in a paper from 1928 about the triviality of isomorphisms, was a response to Russell's structural realism, where basically, the idea was that a scientific theory about some collection of objects is true if it postulates a theory and it postulates a relation over the object, and there's a relation over some objects that the objects are referring to, such that the two relations are isomorphic. So you had this, in Russell's theory, you had this existential quantification over possible relations. And Newman pointed out that if it's just an existential quantification over a relation, you can always find such a relation to make this true. But he also pointed out that obviously this is not an argument when the relations are fixed in advance, when they are the same, for example. And the kind of isomorphisms that we're talking about here, and I think this is important, just means that Newman's challenge here does not apply, because the relation in the language model is cosine distance. The relation, say, in the computer vision model is cosine distance. These are the primary relations in these models. It's basically the only relation that these models care about. So it's an isomorphism across the same relations. So it's really a graph isomorphism and not a set isomorphism. It's also the case that these relations are founded in the sense of Carnap. They're fundamental for these models. They're exploitable in the words of Nick Chi, and they're map inducing in the sense of Alistair Isaac. So these are, we're not talking about any relation here. We're talking about an isomorphism between really important relations in the representational systems. And they're exploited in many ways. So cosine distance is important for nearest neighbor inferences in large language models, but also important for analogical inferences. There's a nice paper by Eli Pavlik's group showing how these large language models do analogical inferences by using vector offset in cosine distance space when they're confronted with out of distribution examples and they can rely on memorization. So it seems that these large language models really use these distances where we find these isomorphisms. Okay, cool. So I think those are probably the most important challenges. I just want to mention a couple of other challenges against sort of seeing, against this sort of symbol view of large language models being able to talk about cats and chops in virtue of having these models. So fundamentally, these are connectionist systems, and one of the standard challenges here is systematicity. And I just wanted to mention that. I think there's already been a lot of pushback against kind of Fodor's claims about connectionism. So the standard one is that connectionist systems can implement classical systems. So if classical systems can be systematic or exhibit compositionality, so can connectionist systems. What I'm more interested in here is just like the convergence results that I presented you, showing that these models tend to converge toward having representations that align really well with other types of representations that we see independently of the language models. It's also the case that the larger and deeper the large language models get, they exhibit increasing systematicity and compositionality. With instruction tuning, compositionality gets better, and there's a lot of prompting strategies if you want to sort of unlock the compositional generalization in large language models. So I think there's reason to believe that, not only is this possible in large language models, but it also sort of falls out of the objectives that we use right now. Another type of challenge that I wanted to mention is from Robert Cummins, and is about unexploited content. Robert Cummins talks about how representations sometimes contain content that we're not aware of, but that upon revisiting the representations enable us to do stuff that we couldn't do before. So one of the example is about a person using a map. So he says, imagine someone who learns to use road maps to find a route from point A to point B. It never occurs to this person to use the map to extract distance information until one day someone suggests that the map shows a shorter route than the one generated. Okay, so the person here is using parts of the representations, but all of a sudden realizes that there's this content in the representations that was not exploited up until this point. So this kind of challenge is a problem for teleosemantics, for example, because selection presupposes the representation is exploited in the first place, but not for large language models because the representations fall out of something else. They fall out of just this predict the next word objective. So in some sense, sort of semantics or the semantics falls out of syntax here. So you could account for unexploited content. Now, I think this is the point where I just want to ask how much time we have. Because
since you've been time sharing with the question and answer period, you're okay. We're just going to continue until we get to what is here noon, which is in 19 minutes.
Okay, great.
You can use it as you wish.
Yeah, sure. Okay, let me go over this relatively fast. So this is another type of challenge that the moment you start thinking of large language models as sort of potentially having aboutness and as theories of how that could come about, one of the problems that's often mentioned is the opacity of these systems. Unlike some of the more classical systems, and I call this Cynthia Bruden's challenge here. So just to sort of talk about for a few minutes why this potentially could be a problem, just want to mention this is Alvin. Alvin is a driverless car, one of the first driverless cars. This is work by at CMU in the 90s. Bean Pomelo, I think the chief architect, and wrote a technical report in which there's a nice anecdote. And the anecdote goes as follows. So Alvin here is it's a car. It has a camera mounted on the top, and there's a neural network steering the wheel. So the network learns correlations between the images and wheel movements. So initially you would have a human driver drive the car, and the neural network would figure out how to correlate the images from the camera on the top of the car with the wheel movements. And then at some point, the neural network is supposed to take over. So the only objective here is to stay on the road. And there's this nice anecdote. You should imagine sort of an autumn scenery, a forest. There's leaves all over the place. There's a ditch along the right-hand side of the road. It's a dirt road, and there's a lot of trees. And the human driver drives. At some point, the neural network takes over, and the car does really well. And then at some point, they get hungry or something. So they turn the car around, and then they let the neural network drive, and it just goes crazy. And they go home and they inspect the neural network, and they realize that all it ever learned was staying left of that ditch on the right-hand side of the road. And this is sort of what Klaus Robert Müller calls the clever Hans effect, that sometimes, you know, what appears to be a smart neural network may have learned some stupid strategy because of spurious correlations in the data. And the question, of course, is whether it's sort of a problem for sort of the claim that these language models have aboutness, that these models are in some sense opaque. Now, in some sense, they're, you know, obviously not black boxes. You can print out all the computations in a large language model, but it's sort of hard to map their dynamics onto explanations. And it's hard to dumb them down. So Cynthia Rudin talks about how, you know, XAI is never going to give you faithful explanations. And for two reasons. One is that oftentimes these models can be computationally irreducible in the sense that there's just going to be no symbol or no simpler equivalent model out there. And also sometimes they can capture stuff that just doesn't map onto our vocabulary because they're capturing something that's subsymbolic. And certainly for the XAI methods that are rely on linear explanations that are sort of linear combinations of concepts, most XAI methods would present you with explanations that are weighted combinations of concepts that are supposed to occur in the input data. Then you have a very, very small hypothesis space all of a sudden. So of course, that is true. And, you know, large language models are complex systems, but they're also trying to model complex systems or complex phenomena. And the question is here whether this is really a problem or not. And of course, you can take different stances here. I'm going with Dan Dennett for a moment. You can sort of have a sort of a physical stance where I guess, you know, the explanation for the behavior in this case would be something like the implementation of the ditch neuron is not excited, and that's why the car is acting out. But there are other stances, like a design stance, the network was trained on biased data, that might be interesting. There's intentional stances, the network's confused, and so on. And to go with Cummins for a little bit, there's, you know, you can try to sort of explain the network by appealing to causal laws and do causal subsumption to laws such as if the ditch neuron fires in position ij, the wheel turns left or something. But there are other types of analysis, like compositional analysis. The network weights here are sparse with a ditch component, for example, or, you know, functional analysis where you say something like a network trained on a giveaway signal will behave erratically in its absence. And that's sort of the level, it seems, that we'll have to explain most systems anyway, most complex systems that have the cognitive capacity of understanding. So in sum, what I'm trying to sort of present here is some arguments for at least saying that this very naive position in the LLM understanding debate to basically kind of say large language models build up these world models. There's ways that these world models could project onto other representations of the world or onto aspects of physical reality. And it's not entirely clear, to me at least, why that kind of simple, naive position would be obviously wrong. It seems that there's a lot of representations that are induced in these models, that they align really well with other representations that are independent of the large language models. The representations seem to do explanatory work. So when these models do analogical inferences in cosine distance space, they rely on these structural similarities. So the structures learned here are exploitable. And it seems that the various challenges from Goodman and Newman and Fodor, potentially Cummins and potentially Rudin, don't really seem, to me at least, like something we have to take seriously in this particular context. That's what I wanted to say. And I hope I'm leaving a little bit of time for questions.
Okay, thank you very much. You did leave a few minutes, and I want to throw it open. And as usual, okay, great. Chris, go ahead. Chris, and then Steve.
Okay. I hope you can hear me.
Yes.
Okay. So yeah, with regards to your question, why shouldn't we just call this understanding? I was wondering if you think of understanding as something like that pertains to humans and machines in the same way, or would you say that, well, for machines, it's really something different? So when you say there's isomorphism, I think there's no question really about that. I mean, everybody agrees that these machines are really able to, find statistical relations that can be mapped onto the word, and that somehow, in that sense, refer to cats or whatever you have. But it's a different question if they understand, and maybe you could say, well, this is just understanding, and at least for machines, that this is all what we can get. But many people say, please, could say something more about understanding. Isn't understanding something that is connected, at least sometimes, with awareness or something? Maybe it's a complex process. Maybe there's several kinds of understanding. So the question, is it the same understanding you attribute to machines, or you find in machines, that humans have, or are there different kinds of understanding?
Right.
Could you cut your slide share first, Andrew, so we can see one another?
Sure.
Thanks. Go ahead.
Thanks. That's a great question. So I guess in general, so first of all, I want to point out that while I'm glad you say that most people agree that these models induce representations that sort of seem alignable with stuff out there, that has not always been the case. I mean, if you read Mitchell's paper, or you read Bender and Kohler's paper, they talk about how these models don't have any they don't have any world knowledge. They don't have any knowledge about the world that would enable them to have semantics. So I think just establishing that there are these structures was an important first step. That said, I'm happy to kind of move the goalpost, and if meaning / understanding, and maybe they refer to different things in the minds of most, mean more than that, I think we should look at exactly what these terms are supposed to mean, and figure out whether this is something that could, in principle, be instantiated in computational systems. I mean, obviously, the kind of language models that I've presented experiments with here are monomodal, and that is a limitation. You ask specifically about awareness or consciousness, and what that means, I guess, is also up for debate. But so let's keep consciousness out of the question. But just like awareness, is there a sense in which, and so I think there's two sort of, first, you need to accept the challenge. You need to say, okay, it is part of meaning to be aware, in some sense, whatever it means. And I think that is maybe worth a conversation too, because I mean, there's a lot of results in psychology showing that, people can construct meaningful sentences and responses, without being consciously aware, either during sleep or during anesthesia or whatever. So I think that's sort of the first step. The second step is to say, okay, so what exactly do we mean by awareness here? Is it just having a self-model and being aware of the fact that you're part of a dialogue here, and that by pointing out or like using the word cat, you're sort of changing the conversation, or is it more than that? I think it's pretty clear that these large language models, or chatbots at least, have some sense of the fact that they are taking part in a conversational game, and they're kind of they have some influence on the environment that the conversation is taking place in.
Okay, so many thanks to everybody. Sorry for the strike. We did fairly well because we could have been shut out completely. So at least we had the session. Thank you for everyone's contributions. See you next